welcome back to session 3. As we mentioned at the beginning of this session, this is an extremely useful, I would expect to be an extremely useful set of tools that we will use throughout our course. One of the most important elements that we will have to use again and again are our random number generators. In section 1.1, we displayed how to create random samples out of a diverse set of possible distributions that come with Maple's statistics package, and some of them that can also be customized by ourselves. Now, in that case, we're just having univariate random samples, but more often than not, we will need to generate multivariate correlated random samples. So in this session, we will take a look at how to do that. And I will jump directly to our interface, but just let me underscore what we've said already in class, that we will use a very useful theorem that comes out of using LU matrix factorization methods. We always start with a correlation matrix, then we apply a decomposition, then we calculate a matrix which we'll call CD, and by post-multiplying our original data set of uncorrelated variables by these matrix, we will end up with a correlated set of random variables that will have the correlation matrix originally put together for this exercise. So here's the step-by-step process. We can also use singular value decomposition techniques to achieve a similar result. I will obviate this part since it's been already seen in class. What we display here is a set of bivariate distributions. So starting from bivariate normal, uncorrelated, then we put together or consider a correlation coefficient, which can go from 0 to 1, and then we end up with samples that start from uncorrelated variables and end up with some correlation here. No? This correlation is very close to 1, and well, it looks really nice. We do the same for a bivariate long normal, but I would like to focus a little bit of our attention to a three normal distribution, three variable normal distribution. So we will start with a correlation matrix. I put here a few sliders, and these sliders allow us to design our correlation matrix. So if I put everything around 0 correlation between these three random variables, we will end up with a correlation matrix that has the ones in the diagonal, and then something very close to 0 around here. I am kind of not very good at putting exactly our sliders in position, but you get the idea. So it's pretty close to 0, all these cross correlations, and in the sliders below, I have the variances for each one of the three random variables. Then what we have is an input that is shown here of the three random variables, 1, 2, and 3, and this is the data set that comes, the sample that comes from this specification. And now what we will see is how the random sample changes as we change also the correlation between variables. So this is going to be very nice. Notice that the graph that we are using here is known as agglomeration graph. So in each one of these cubes, we are, let's say, condensing a relatively large number of data points, and this is done in a way that makes it easier to visualize data. These graphs are commonly used in problems that have large numbers of observations if I remember correctly, they were initially used by meteorologists. So now we are taking advantage of that here to visualize. Now let's start playing around with our correlation matrix. So I can change the correlation here. It's 0.6, so 0.7. So now we see the correlation 1, 2 to 0.7. Let's play around with something of negative correlation here. And we can also play around with, again, relative large correlation here. So now our correlation matrix looks like this. Our original data sample looks like this, but now the correlated sample, we're taking 5,000 samples or draws in this example. Now it looks like this. This is pretty nice, no? So as we play around with correlation, then the distribution changes like this. We can end up with two negatively correlated pieces of random variables. And look at this. This is very, very nice. Very nice. Negatively correlated between each other, right? And if we go again to a random sample of uncorrelated variables, this is what we get. So the great message here is that we've been able to produce random samples of correlated variables out of essentially any form of distribution that we want to start with, and this will be very useful. So thank you very much. We will see each other again for session 4. Have a good afternoon.